Okay, so what I would say is you're trying to prioritize, because I know I'm probably not the only test you have this week either. I would study as if you're studying for the test and then try the practice test. I wouldn't, it's tempting to just do the practice test and then just kind of learn just from the practice test, but I want you to kind of study as if you've studied and then sit down and do the practice test and then see what's missing, okay? If you can do the practice test, then, and you kind of understand the concepts around these questions, so not just this question in particular, but the concepts around this question. For example, how do you determine if it's a function or not? We use the vertical line test, right? So then you would say, by the vertical line test, it only intersects this graph once, therefore it is a function, right? And so kind of having that, that theory behind each of those questions, right? And then you'll apply that same theory to the test, okay? So if you've studied and you feel like, okay, I think I'm ready, and then you sit down and you do the practice test. Now I'm gonna keep it the same length. So you should have lots of time because we have a half hour more. And so, because I feel like it was a little bit long last year, and so I'm gonna keep the same length. I'm gonna add one question. And so I think you'll have lots of time, so you can kind of take it easy. I mean, yeah. So let's just do a brief run through of the practice, and then we'll kind of, you'll get a graph. Is this a function? This is way back to chapter 1, beginning of chapter 1. Talk over the air. It's okay. Usually there's more stragglers, but maybe not after a long weekend. Everyone's like, no thanks. So just some concepts, right? What does it mean to be a function? What does it mean to be one-to-one? Only on the domain shown, otherwise we can't really say. Interval notation, okay? Where is it one-to-one? Kind of a hint as to the previous one. Interval notation, so domain and range. And then we're going to use the graph to evaluate the function. Now that's kind of approximate, right? Because you won't have a very good grid, but I try to pick points that are kind of obvious. And then solving, right? Evaluating and solving a function. So here we have a function as a graph. Then I give you a graph or a function as a table, right? And then eventually we'll move into a function as a mathematical function, right? And so same way that we moved through the course. Okay? And so why does it represent a function? Is it one-to-one? Evaluate something from the table, solve something from the table, right? Kind of nothing crazy in my opinion. That's not what tests are about, right? I'm not gonna try to challenge you too much. The challenge is sitting down and having to do all these questions in a row, right? That's the challenge. I'm not trying to put out crazy hard questions or anything, right? And so something to keep in mind. Oh yeah. So here we have a graph and we have a piecewise function, right? And so what you're going to do is you're going to write out the piecewise function with the appropriate domains. And for space reasons, I would put it beside the graph just because I am cheap on paper. So first things first, we move from the left to the right, right? And so what we need to find is we need to find the equation of this, this line here, right? Which means what? We need to find the slope and the y-intercept of this line, right? And so the slope is the rise over the run. Rise looks like it's 3. Run looks like it's what? Also 3. It's negative. So I've got a slope of 1, right? And you can do that using the formula on your formula sheet, which, right, this one here, it's going to be the first thing. The average rate of change is the slope, right? And so we've got all these different ways of writing it, whatever you prefer, right? We've been kind of focusing on f of b minus f of a minus b over minus a, or over b minus a, but maybe in this case, y2 minus y1 over x2 minus x1 makes more sense, right? Pick 2 points on the line, maybe those endpoints, and calculate the slope. And then you can find the intercept where it crosses. There's actually quite a bit more work here. Y equals x plus b, and then we can put in any point. Let's do -3, -1. -1 is x minus 3. So then x. Oh, sorry. Oh gosh. Wakey, wakey, Emily. Not x. 1 times, oh my gosh. 1x plus b. There we go. Using this point here is at -3, -1. So if y is -1, 1 times -3 plus b, then b is going to be -1 plus 3, which is 2. But it's -1 slope. Oh my gosh. So it's positive. I need a do-over and maybe a coffee. -1 minus 3, -4, which if you trace this down, checks out. There. Okay. Way too much floundering. -x minus 4 on what interval? On x from -6 to -3, including both those endpoints. Right. So x is between -6 and -3 inclusive, right? Phew, then I have a horizontal line. That's nice. And let's tackle the domain first, right? So from -3, but not including -3, up to and including x is equal to 2. This function or this line is at y equals -2. So this portion or this piece is just -2. F of x is -2 on that domain. Then you do the same thing for this next domain, which is from 2, not including 2, up to and including 6, because it's a solid dot. We have to find this line. Maybe we'll do it properly this time. This is at 6, -1, because I obviously can't handle it, to -3. The slope is going to be -1 minus -3 divided by 6 minus 2. -1 plus 4 is 3 divided by 4. Check. Should it be positive? Yes, it should be, because it's moving up.
Should that be 2 over 4?
-1 plus 3. Yes, 2 over 4. So 1/2. Nice, thank you. Then from here, we have y equals 1/2 x plus b. And you can pick either one of these points, it doesn't matter. Let's do 2 and -3, kind of convenient. Then I have -3 is 1/2 times 2 plus b. 2 over 2 is going to cancel to 1. So then -3 minus 1, so b is -4 again, which if you check, kind of makes sense that it would continue across -4. So then y equals mx plus b 1/2 x minus 4 is that last piece of the piecewise function. Guess I should give you more space. I'll bring scrap paper, but just make sure that you can write everything on the test as much as you can, because it's just easier for me to mark. Okay, nice. I feel like I'm math warmed up now. Then you're going to find the domain. You're going to write it in interval notation, right? So figure out what values of x to exclude, and then write out the domain in interval notation. Things to remember, right? We can't divide by 0. So any x that makes you divide by 0, you have to exclude from the domain. And we can't take the square root of a negative number, right? We're only going to deal with square roots, any even root, but you're finding the domain, so any values of x that you could put into each of these equations.
Oh, okay. So and like b would be always x except all real numbers except all real positive numbers. Yeah, can we review one of these?
Let's do b. And I have posted the solutions, so you're not going to be lost if we don't do all of them. I don't mind at all doing some of these, but because I think it's good, but don't worry if there's one that you're like, oh no, wish we'd done that one. So here, remember that we can't take the square root of a negative. Right? That's what we need to remember here. And also here, note, we can't divide by 0. And then notice, so here on the sides in the boxes, I've got the marks. Approximate marks, I can't remember if I adjusted some of these, if they were more work than I anticipated. But generally kind of a good guide for 1 mark, 2 marks. Because here you're dealing with a square root and division. Whoa, gotta do a mashup. Okay, so here, we need to make sure that 3 minus 9x has to be greater than or equal to 0. So we can take the square root of 0. You can try it on your calculator, it works. And so 3 minus 9x has to be greater than or equal to 0. I mean, technically, yes. Just a little bit more work. Just gonna do a little bit, which means that 3 has to be greater than or equal to 9x. There's lots of ways that you can solve this. So if you don't want to work with the inequality, what you could do is you could set it equal to 0 and then use a sign chart to figure out where it's less than 0 on which side of that x you're going to be less than 0, right? So play around with it and see which way you like it. I'm going to use the inequality, but like I said, there's lots of ways you can do it if you don't like the inequality. So then divide by 9, I get 3 divided by 9 has to be greater than or equal to x. So x has to be less than or equal to 1/3. Might be helpful to draw this on a number line. Right? 1/3, let's put it there. Kind of hard to see, right? But x has to be less than 1/3. And so where am I? Less than or equal to, so I'm going to do a full dot, and then I want to be on this side. So that's what I mean by, if you want, you can set it equal to 0 and find that x equals 1/3, and then just put in test points on either side, right? If it's less than 0, then you take it out, and if it's greater than 0, then you leave it in, or I guess vice versa. Because what I mean by that is, let's do at 0. 3 minus 9 times 0 is 3. What if we do -1? 3 minus 9 times -1 is 3 plus 9, which is what? Usually 12. So it's positive, right? Which is what we wanted. Whereas if you check on this side, right, let's put in, I don't know, could do 1, let's do 2, just to pick a point on the other side of 1/2 or 1/3. 3 minus 9 times 2, oh boy, bad math, Emily. Okay, 3 minus 18, there's no way of knowing. There is, but maybe you guys can check. It's 2, 3 minus that is -15, which is bad. Right? So then you've confirmed. So really, all you need to do for this question is this one, and then write it out in interval notation. Okay. But then it's always nice to be able to check your work and just make sure that what you're doing, you're kind of happy with what you're answering. Okay. And so you can even try it at 1/3 if you want to, but then the interval notation is everything up to and including 1/3. So the interval notation for that looks like this: -∞ up to 1/3 square bracket. Infinity always has a round bracket around it. Right? So in terms of your answer, all you need are these things, but it might be nice to put the other things on there as well. Okay. Okay. So the domain, I'll do a square root, I'll do a fraction, I'll do a mashup, just like that. Just different functions. And if you can believe it, these are all stolen from your assignments that you have been doing. They look different though when they're on paper, I think.
But that's when you're just writing it on your own.
Yeah, and it's like, hey, it's all permanent here, not just in a Moodle quiz. Right? And so that's why I wanted to give you a printout, but they are just stolen from assignment questions. different numbers, obviously. Average rate of change of a function on some interval. Now, on that formula sheet, we've got the average rate of change. So given a function f of x, the average rate of change on an interval a, b is f of b minus f of a over b minus a, right? So that's the one that I would choose to do these questions that you're about to do. Right. Then we talked about properties of graphs, right? And so you're going to use interval notation. A lot of interval notation, mostly because I think it's the simplest of kind of the simplest way of communicating inequalities or kind of ranges, right? Otherwise, you would have to do the x less than or equal to blah, 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 and that's annoying. Or set builder notation, which is even worse. And so interval notation, I use interval notation just because it's the easiest. But I mean, if you wanted to use set builder notation, you could, but I don't see why you would. Where is it increasing? Where is this thing decreasing? Now, obviously, like I said, the points are not going to be bang on, and so just kind of approximately. Yep.
I'm giving 2 points, right?
So where is it increasing? Let's say roughly -2 to roughly 0.
Only be like the bottom there to 4 because it starts to go down, doesn't it?
Yeah, so here it's going to be increasing all the way here. So it'll have a positive slope from roughly, let's do roughly -2 to roughly 0. I'll highlight the approximately.
In our notes, there was like that it was in the middle of it.
Oh, the inflection point. So the inflection point is where it changes from concave up.
Yeah.
So here, concave up to concave down. And I think is concave up, is concave down, has an inflection point.
Oh, so they're different.
Yeah, the increasing is just still just attached to the slope.
So the inflection point would be -1,4.
Yes. Here's an inflection point. And that's it.
So
nice. So just kind of properties of graphs, right? But see how sloppy I was with this interval from -2 to 0-ish. Use round brackets because I was being sloppy, but so just approximately, because it's really hard to make a graph that satisfies all the criteria easily. And so just be approximate. Okay. So where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? And then has one or more inflection points, right? Where it changes from concave up to concave down. Given a table of values, do some function composition, 1 mark each. Start in the middle, right? G of 6 is what? G of 6 is 7, which means that this must be f of 7. f of 7 is 9. Right? Those. I had one of these on here for easy marks last year, but then I think I was kind of feeling bad because I'm like, hey, these were supposed to be like easy marks. And then I think everyone had focused on harder things. So maybe give this a brush off.
So for f of 0, or say answer 7 as well, or yeah.
This one maybe?
Yeah.
Yeah. So f of 0, you're going to evaluate f of 0 first, which is 6. So then you want f of 6. F of 6 is 2. So just remembering to read it, evaluate from the inside out. Nice. Sneaky. I feel like one of these, if anyone has the solutions, maybe one was a little bit more intense than I anticipated. F of g of x, wherever you see an x in f of x, you're going to stuff in g of x, right? 1 divided by 5 over x plus 6, and then minus 6. All right, simplify that. And then what's the domain? From the first part, x can't be 0, right? First, you need to have a valid g to stuff into f, right? And so first thing you need to deal with is, okay, we need to figure out what the domain of g is, and then you can figure out what the overall domain is. But usually it's satisfied by the first one.
For g, are we just going to plug it into the x with the x there?
Yeah, so here, f of g of x is 1 divided by 5 over x plus 6, and then minus 6, which you can simplify to 1 over 5 over x, I guess plus 6 minus 6, so just 5 over x. From before, x can't be 0, and that's still the case. The domain of g is that x can't be 0. That's still our only condition here, and we can simplify this as 1 over 1 times x over 5, right? A fraction over a fraction. Flip and multiply, which means x over 5. With the domain. Let's do it in interval notation, even though it doesn't specify. Negative infinity up to 0, not including 0. Union 0 to infinity. We're just taking a break at 0. Yeah. Yeah, because we, the restriction on f of g of x is just 5 over x plus 6 minus 6 can't be 0. But that can't happen if x can't be 0 coming into it. And so, well, it wouldn't be 0 anyway. So, so then you can't have this be 0, but you've already handled that up here. So then you just simplify. Nice. And you flip them. Do the same thing over again. Yeah, once you get the fraction done. Okay. here's what I decided to do for, because I don't like doing transformations kind of under pressure, but you will have the outline on your formula sheet. And so you're going to give g of x in terms of f of x. If the graph of g is obtained by vertically stretching f by a factor of 4, then shifting the graph of f to the right 2 units and upward 7 units. Okay? And so, okay, let's see here. I do want to leave you to try that one on your own. Okay? But you've got the vertical shift. What does a vertical shift look like? What does a horizontal shift look like? Right? What does a reflection, vertical or horizontal, look like?
It's a stretching stuff. I feel
Yeah, the stretching's the hard part, right? So I encourage you to try it. You've got the solutions, right? Because it's one of those things where if I'm standing up here and I'm telling you how to do it, it's like, oh yeah, that totally makes sense. Totally makes sense. Got it. And then you go to do it yourself and it's quite different, right? But you'll have one of these printouts. Okay. And I give you a function, right? We know what x minus 7 squared might look like, right? X squared is the root function or the core function. And then we've shifted it over to the right by 7, but that's it, right? And so we know what this thing looks like. Right? Got a little gap there. And here, this should say find a domain on which it's 1-to-1 and non-decreasing. Okay. Try to go for the biggest domain. So if it's 1-to-1, right, then it has to pass the horizontal line test, right? And non-decreasing means it's increasing, right? And so your options start here at 7 and then any interval from 7 to infinity. But usually I would just anticipate that you would put 7 to infinity. And then that's the largest possible domain. But
that's the answer.
yeah. Okay. Technically, you could go 7 to 8, 7 to 9, 8 to 9. Get weird with it. But I would maybe I'll add find the largest possible domain, and then it'll be kind of more straightforward, at least from a marking perspective. Then I want you to find the inverse on this restricted domain. So remember, x is greater than 7, right? Finding the inverse, we did that kind of multiple steps, right? Switch your x's and your y's, and then you solve for y again, and then rewrite it as a new function. It's quite a bit of work, but because it's difficult, I kind of struggle. So do I make a hard question worth a lot of marks, or to potentially drag you down, or not very many? And so I tend to limit my questions to be out of 2 marks, even if they're, kind of tricky. But try it, see how it goes. If f of x is a linear function, and we're given that f of -3 is 2 and f of 1 is -2, then I want you to find an equation for f of x. We already did that with the piecewise functions, right? We were given 2 points, or we took 2 points on the piecewise function, those lines, right? And so we've already done this. This is just a different way of doing the same thing, right? We're asking you to do the same thing. Find the x and y intercepts of this equation. Well, the x-intercepts, right, that's where y is 0, and the y-intercept is where x is 0. Right? Let's see here. Why is it 4 marks? I wonder if there's something in the... I haven't looked at the solutions in a long time. I just tossed them up there. Yeah. Why? More of a note to myself, too. That doesn't make sense. Huh. If there was squares, maybe, but there isn't. I'll look into that one. But it is just as good as you think. And by good, I mean easy. Okay. Now I describe 2 lines with 2 points each, right? All you need for a line is 2 points, and then you can find the slope and the intercept, and you can build that line. Now, find the slope of line 1, find the slope of line 2. Right? You can do that. Explain why these lines are or are not parallel, right? Or perpendicular. Right, so what do you need to remember? If they're parallel, they have the same slope. So then you would, if the slopes are the same, then you would say because slope of line 1 is the same as the slope of line 2, therefore they are parallel, right? Also think about perpendicular, right? M1 times M2 has to be -1 if they're perpendicular. Or this is when M1 is equal to M2, or perpendicular. This isn't on your formula sheet, right? So it's one of those things that you need to remember. But I think it's...
So basically, the slope is -1 over.
Yeah, you can rearrange it if you want. Yeah, totally. Okay. Write an equation for a line perpendicular. So that's when you're going to need to use that M1 times M2 is -1, right? Or maybe M2 is -1 over M1. If you can find the slope of the first one and then do -1 over that slope, right? Then that's the slope of the second one. So passing through some point, you'll need that to find the intercept. Okay. Intersections. Find the point where the line, where f of x intersects g of x. Right? You can always check your work with Desmos, right? You won't have Desmos on the test. Uh-oh. What can you do? Well, what will you do? Nice. That's where they intersect. Then you're going to find the point of x that makes that true, right? And then you can solve for y using either equations. And just remember, if you put in the same value of x, you should get the same value of y if you've solved it properly. A regression was run. So that's that day that we had a little bit of Excel practice, right? And so it's a linear regression. So it's saying that the relationship is y equals ax plus b, and it gives you a and it gives you b. Also gives you the r squared and the r, which is the correlation, right? You're going to use it to predict the number of sit-ups of a person who watches 11 hours of TV. This is also where I'm going to add a question which isn't on here. Curveball. I'm telling you, I'm adding it. Given an Excel scatter plot with the regression equation and R squared, make a prediction and find the correlation. And find the correlation. Yes, which is the square root of R squared. And then you tack on a negative if it's negative, right? Because squaring is going to make it positive, so you lose that, but you'll have the graph. So if it's positive, you keep it positive, and if it's negative, you tack on a negative. Moving backwards. And let's throw in some interpolation versus extrapolation. Yeah. Absolute value functions. Right. 2x minus 1 can either be positive 11 or 2x minus 1 can be negative 11, right? And so there's going to be two values of x, right? Because what does this look like? You've got your line. Sure, it's a little bit steeper, but it's been moved over 1 to the right. And then we want to find where does it equal 11 if that line is at 11. So you're going to have 2 points because the absolute value function is a piecewise function. Find the horizontal intercepts of this function. The horizontal intercept is where y is equal to 0, right? So the values of x where the output is 0. You do need to know that, right, to do the question, but you know that. Solve the absolute value of x minus 2 is greater than 9, right? And give your answer as an interval, right, in interval notation. This is one of those where we use the sign chart, right? If you're very confident in your visualizing of the absolute value of x minus 2, where is it greater than 9, then you've got kind of a head start. I don't need to see the sign chart, but we did use a sign chart to figure out what it might look like. So x minus 2 has been shifted over 2 units. And we want to know where is it greater than 9. So that's this and this interval. Right? So we use the sign chart. You don't have to, but I think it's kind of the safest way to do it.
Yeah, for those, sorry, we were doing those, like, that'd be like x minus 2, whatever, equals minus 9, and what's x minus 2?
Yeah, so here, what you're gonna do is you're gonna have the absolute value of x minus 2 has to be greater than 9. Now, what I do is I kind of split this up and say, okay, I'm going to find the points where it actually intersects because those are kind of break points. And I find it's a lot easier to deal with an equal sign than an inequality, right? And so here, x minus 2 is negative 9 or x minus 2 is positive 9. So x x is -9 plus 2, -7, which means I drew this bad. Probably over here. And 9 plus 2 is 11. Then on my number line, I'm going to toss down a 0 just for reference. And then I've got a cutoff point at -7 and one at 11. And then you're going to see where x minus 2 is greater than 9. So you pick a point in each of these regions, right? Let's say -10. -10 minus 2 is -12, which is wrong. Negative. Oh, sorry. We need the absolute values, of course. Why did I know it was wrong? Because I just sketched it out. And I'm anticipating that this region that I'm testing right now should be one of the regions that I want, right? And so -10 minus 2 is -12, but the absolute value of that is 12, which is greater than 9. So that region's good. And then if I use, let's use 0. Use a different color here. There. The absolute value of x minus 2 at 0 is 0 minus 2. So -2, which is 2, which is not greater than 9. So it's a baddie region. Baddie. And then if we pick a point outside of 11, let's do 12 for simplicity. The absolute value of 12 minus 2 is 10, which is greater than 9. So that's good. So then the region, remembering that it cannot include 9, right? And so we found the points where it equals 9, but that means that we have to exclude those points from our interval. All right, and so I've got open dot, and out towards infinity. Now, what does that look like as an interval? -infinity up to -7, open bracket or round bracket, union, and then pick up at 11, but not at 11, going to infinity. And that's it. Feels like a lot, Emily. I know. Something for everyone, I think. But then we started polynomials, but polynomials aren't on the test. All right, we'll save those for test 2. Any other questions about? Oh, and I'm realizing maybe I should go to, although everyone in Zoom knows that I can't see any. Okay, but just in case. Wait, what? Thought I should check. Probably should have told them I was going to check. Oh. No questions? No. Hopefully it feels pretty reasonable. Highs and lows, maybe, but generally reasonable.
I think it's might just be my brain. I think like most of that feels like it's chapter 1 mostly.
Yeah. Well, because chapter 2 is just on lines. So anytime we talk about lines, that's chapter 2. But it seems kind of so easy because we cover a lot of ground in chapter 1.
Yeah.
Right? Okay. So I'll post those notes that I made on the practice.
Sure, I just have one question about number 16.
Sure. Where is it? 16. Yeah.
And he is just information that's just thrown in, but we have our R2 and our R.
Yep.
I don't recall what those are.
So R2 is the coefficient of determination or something. Usually we just call it R squared. I know the definition of R squared. That doesn't help us. It's the percentage of variability in Y explained by the least squares regression line on X. That doesn't really help us, but R squared tells us how well the line fits the data. A high R squared, so an R squared, so R squared is a percentage. So that means that 72.25% of the activity is captured by this line, sort of. But effectively, that's what's going on. And so a high R squared, so an R squared close to 1 means that this line is doing a really good job of capturing any activity, and also it's going to yield good predictions, right? And so a high R squared yields good predictions. Close to one.
Would be perfect. Is that the case?
Say that again, sorry.
So if it was like R2 squared was 1, that means it would be correct exactly.
So yeah, what that means is that every single point is on a line, right? Which is not that fun to model, but it does happen if you have a machine that's consistently producing, right? Then there's no variability there, right? It's just cranking out, I don't know. For some reason, I'm thinking one t-shirt a minute or something. I don't know, whatever. But usually we have kind of some variability. And this R squared 0.7225 is quite high. I've seen published papers where they've used like 20%, which is terrible. And so it does happen, but you want to aim for about 60% as kind of your minimum. It depends on what it is you're measuring. If there is a lot of variability, then sometimes you're kind of hooped anyways. But yeah, for us, we want a high R squared, and that's all we care about for now.
Like in relation to a question, it's saying that it's
Yeah. The only way that I'm going to make you use R squared is to find the correlation, right? So knowing that relationship between the correlation, here, I'll do this. The correlation, if the correlation is negative 0.85, then R squared, or capital R squared, somehow it grows up when you square it, typically is the notation. But if you do negative 0.85, but do the negative in brackets, otherwise it'll put it on the outside, squared, then I get 0.7225. So then vice versa, if you take the square root of 0.7225, oops. you're going to get back to 0.85. But if you have the relationship, right, then you need to add on that negative. Here also, we have a negative slope. So even without the graph, you'd have to tack on that negative. But for us in this course, I'm just expecting you to know this relationship that, okay, the correlation is between -1 and 1. And if I square it, I get r squared. And if I take the square root of r squared, I get back to the correlation.
That's what this add a question, is that what that's about?
Yeah, so here, I'm going to give you an Excel scatter plot. Now let's see, where did I have? I feel like if, where's my?
That one had one at the top.
It did, but not the graph. Let's see if I can. I didn't open it since. So I'll give you a plot like this. Oh, enjoying Excel. How come it's not saying that on my end? I have to show you what I'm looking at. I'm looking at just ready to go. No problems here. Okay. Can I? Okay. Starting again. Enjoying Excel. Oh, well. Yeah, not. Yeah, less and less each moment. Okay, let me see if I can quit this. Start fresh. Okay. Phew. So I'm going to give you something like this. With this, I don't have a pointer on here, so with the regression equation and the r squared. I'm going to make you use the regression equation to make a prediction. I'll ask you, is this an interpolation or an extrapolation? Right? If the x that I'm getting you to put into this line is somewhere here, then it's an interpolation. If it's outside, it's an extrapolation. Right? And then find the correlation. How about this? I'll be nice. I'll make it a positive relationship. So you get the r squared. You have to make sure, okay, I've got a positive relationship. So when I take the square root of this guy, then I can just keep it positive. So that's the one I'm adding kind of secretly, I guess. All the other ones are served up on a platter. Says I know. Okay. I started putting together, and I haven't posted it. But do you guys know how to store stuff on your calculators? No? Do you have a calculator that looks kind of like this? Mine is the older version, white one, but I think this is the one that they're selling in the bookstore now. Anything that looks like this, what you want to be looking for is something like this, kind of a STO or a recall button. Almost every scientific calculator has some sort of store function. Okay. And so on mine, the STO is the big one and the recall is above, but doesn't matter. So you're going to be able to store values and then recall those values later in your calculations. Just saves you a lot of typing and thinking, maybe. So I took a screenshot of this. It's on the ferry. I was like, oh, you know what would be way better than anything else? Talking about calculator functions. All right, so on this calculator, use the store function here, which is obviously a shift function because it's in yellow. And so to access this, you have to go shift and then hit that button. And then what you have are options. So we're going to have slots that you can store stuff in. Okay, A, B, C, D, E, F, and I think you can store in M, but I'm not quite sure. So usually A, B, C, D, E, F is enough. And so whatever you have on the screen that you want to store, you're going to go shift, store, and then put it in one of these slots. If you want to, in your work, you can just write, I'm going to store this in A. That's an indication to me that, okay, I know where I'm putting this thing, but also it means that you don't have to write out all the values because you're telling me that you're going to use the exact values in your calculation. Right? So then I'm not worried about rounding. So it's both to remind yourself where you put it, okay? But also to show me that you're going to be working with the exact value. Okay? So then if you want to use a value that's in A or B or C or D or whatever, then you need to recall it. Okay? So then you can go recall A. So you can do 2 plus recall A or something like that, and it'll just put in whatever you had in A. Another one that I use quite a bit is the answer button. It'll only recall the previous answer, right? But I do use that one quite a bit, and I tend to line up my calculations so that I can kind of use the previous answer so I don't have to keep typing it in. And so that one's a really, really handy button to have too, and it just inserts the previous answer that was on the screen. Nice. So play around with those.
Yeah, I'm trying to get to. I'm trying to push random numbers.
Yeah.
Push a number set it store.
Yeah. Are you on one like this? Does it look exactly like this one?
My recall store
are
just like that there.
Okay. Yeah, so then you need to hit the shift first to get to the store function.
That's my number already.
Yeah, whatever's on the screen is what's going to be stored.
Okay.
Yeah.
Equals that?
No. Let me see. Let's do 4 divided by 5. Store in A. No, it seems to just do it without an equal sign on mine. But it is worth trying.
Okay, so if you hit store, then you always do alpha recall. Oh, no, just recall.
Yeah, let's see which one.
Instead of recall. Yeah, so I did that hit store. And do I do alpha and like say A?
I think you can just go, you can just hit A, B, C, and it'll go 4 over 5. Is it not in A?
Oh, so on there.
Yeah, so now if you go recall A, it says it's
okay.
I bring this up now because we're going to head into some bigger solves where we'll want to save some answers, store some answers, and reuse them. And so I want to be able to use this kind of shorthand notation where I've stored things. But then I don't have to write out all the values either. So definitely play around with that because that is going to be very useful. What's some other things that we have on here? I don't think there was another thing, but whatever. Any questions before we start section 3.2, which is also not on the test? test 2, but not this test coming up. Yeah. So last week, we looked at polynomial functions, right? And so kind of a little bit of review here. We talked about polynomial functions. We established some terminology around polynomial functions. A polynomial function is something like a n x to the n plus a n minus 1 x to the n minus 1 all the way down to a 2x squared plus a 1x to the 1, but we don't write it, plus a 0 times x to the 0, but x to the 0 is 1, right? All things that we talked about last day. We talked about, okay, whatever the highest degree is, notice that these powers of x are decreasing as we move through, right? And so this term, we put a lot of stock in this term. This is the leading term, right? The leading term with a leading coefficient, but also the degree, right? The degree n. Quadratic functions are polynomials degree 2. Nothing crazy, right? And so quadratic functions, not polynomial. Quadratic functions are polynomials degree 2, which is really just this chunk at best, right? Some coefficient times x squared plus a coefficient times x plus some constant. What we're going to find in this section is we're really able to ramp up kind of our word problems as soon as we introduce quadratics. Okay. And so got this problem that we'll start off with. I'll do a little, I guess, end of review here. Jump right into it. Looks like there's a line missing, I think. What I want to do is just give you a couple of minutes to try it on your own, right? Because mapping out the problem, trying to figure it out on your own is probably the hardest part. I'm going to pause the recording for that. And let's go. Okay. Like I said, mapping this out, probably the hardest part. First thing, we have, we're told that it's a rectangular space. So let's do some sort of rectangular space like this. We know she's got a total of 80 feet of wire fencing to enclose 3 sides. And then the 4th side is going to be against the backyard fence. It does also say that find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. So that means that, okay, one of these has to be the existing fence, right? So this one already exists. Wanted to make it all grayed out so that it doesn't count anymore. Okay. So we're going to prop it up against this existing fence, right? Because if the sides of fencing perpendicular, right? So that's this line, bless you, and this line, they have to have a length of L. So it's all kind of coming together here. So that means that we don't need any fencing here because it already exists. There's a total of 80 feet of wire fencing. And if this is L and this is L, because in order to be a rectangle, they have to be the same length, then this length must be 80 minus L minus L. Right? I've already used up L and L. And so this must be 80 minus 2L. The area of a rectangle is the width times the height, right? One of the sides times one of the sides. And so what we have is the area in terms of L, the length of one of the sides, is going to be L times 80 minus 2L. And I'll clean up that too. Right. Width times the height or some version of that, doesn't matter, multiplying. A times B is the same as B times L. So then the area is going to be 80L minus 2L squared. If I rewrite my powers of L in decreasing order, right, I get this quadratic negative 2L squared plus 80L, right? This is a quadratic, right? It's a polynomial degree 2. What else do we know about this thing? I know that the overall function is L squared, right? And if I let my L be my x's on a graph, then I can draw this maybe something like this, focusing on the negative 2L squared. Right? There's some other things, but in general, negative 2L squared, the negative 2 takes my parabola and it flips it upside down. Right? And so this thing might look something like that. Yeah. Maybe I should draw it in Desmos instead. Let's. How about that? Negative 2x squared plus 80x. Just treating my L's as if they're x's. Whoa. Get this nasty parabola. With a peak at a length of 20 and an area of 800. Yeah. Wait. Come on. I'm trying to move this screen over there. But in general, we know what this thing looks like, right? It's a parabola, it's been flipped upside down, and it's going to have a vertex. This peak is called a vertex. Now the vertex, if we think about maybe a nicer looking version of this parabola, might be something like this. If we have L here and the output is A of L, and we're told that the vertex is that 2800, that means just by looking at this graph here, the output is the area, right? The area of the rectangle. Right? And so for each value of L that you put in, right, we're going to get different areas. Now this becomes an optimization problem, because at the vertex, I reach the maximum. Right? So notice we reach the maximum area at the vertex when L is equal to 20. So if we let this be 20, this be 20, then I have 80 minus 40 left over here. So I have 40 as my width. It's kind of a sneak preview of what we're about to do. Finding the vertex is going to help us optimize problems. And optimization is its own field in math, but it's nice to have a little bit of an overview. What was the question? Find the formula for the area enclosed by the fence. Well, we already did that here, and then I took it even further. Nice. Okay. So we'll come back to that example, but for now, it's pretty good. Introduce the vertex. We have two different forms of quadratic functions. So we're used to seeing the standard form. So the standard form of a quadratic is something like ax squared plus bx plus c. But there's also the transformation form of a quadratic. And let me see if I can. Okay. Can't remember where I wanted to add something here, but so the transformation form of the quadratic is just ax squared plus bx plus c, but rewritten as a times x minus h squared plus k. Now notice the transformation form makes it way more obvious what the manipulations that were done to x squared are, right? X squared has been moved over to the right by h units and up k units. Okay? And that is exactly where the vertex is. Okay? So the vertex of a quadratic location function is located at hk, where h and k are the numbers in the transformation form of the function. Okay? So we didn't write our area in the transformation form, but we use Desmos to find the vertex. But now what we're going to do is we're going to rewrite this in transformation form to find the vertex that way. Okay. I feel like I wanted to insert something here, but I didn't make a note to myself, so I guess not. Can't be trusted. So if we want to find the vertex of f of x is 2 times x minus 3 squared plus 1. Now this is in transformation form. And so what we have, right, is I'm just going to write out below a times x minus h squared plus k. we're told that A is equal to 2, H is equal to 3, and you want to pay attention to the sign here, right? Has to be X minus H. So if it was X plus 3, in that case, H would be -3, right? So you want to, I think I've got one, yeah, just the next one, so don't worry. And then K is 1. So now the vertex, or you could have just gone straight to the vertex, I guess. The vertex is at HK, which is at 3, 1. What's the general form of this thing look like? So I have a parabola and A is positive, so it's facing up still, and it's been shifted over to the right 3 units and up 1 unit. So this vertex has to be the minimum now, right? If it's still facing up, so here, it's facing up, it's been moved over 3 units, up 1 unit, something like this. And so now 3, 1 is the minimum. So if you wanted to minimize the function, it would be the vertex. Right? And we can draw it in Desmos if we want to. We'll do the original function 2 times x minus 3 squared plus 1. And I'm zoomed way out. Come on. But there it is. Which is what we were able to sketch out. No, there. So in this case, because the parabola is facing up, right, the vertex is a minimum. What if we want to find the vertex of this function? Right, this looks like transformation form, which is way easier for finding the vertex, right? Which is a times x minus h squared plus k. It's plus k, yeah. So jotting down a is -3, which means it's facing down, right? So that's what the A tells us mostly, is if it's facing up or if it's facing down. H is -2, right? Since x minus h has to be x plus 2. So if I subtract x from both sides, then I get -h is 2, or h is -2. You don't need to do this work if you're okay with just saying, okay, if I have x plus 2, then x minus h must be -2, right? But this is technically y. And then k is -1. Putting the vertex is at HK, which is -2, -1. And from visualizing this thing, that must be oops, -2, -1. It's facing downwards, making this a minimum. Sorry. Didn't give you time to stop me though. A maximum. Okay. Let's see. Okay, this is where I kind of started saving some space. I'm going to add a page here. And I'm going to move these down. So moving between standard form was that ax squared plus bx plus c. Let's remind ourselves of that first. Then the vertex hk, we can find h by doing negative b over 2a. And we can find k by evaluating f at h, which is the same thing as evaluating the function at negative b over 2a. I'll give you this on the test. It does mean that you need to know what standard form means, right? And where you get these A's and B's from and how to use them. But I do want to show you just how we can move between the two if you had to, right? So from, the trick is to move from transformation form into standard form. And so show that a times x minus h squared plus k is equal to the same thing as ax squared plus b. Oh, it doesn't, Okay, I changed my mind. Not show that, but rather rewrite this function. And let's stitch this in standard form. That's what I wanted. And what we'll see is the h and the k will be able to solve for those like this. So if you have a times x minus h squared plus k, first thing I'm going to do is I'm going to expand the x minus h squared. So I have a times x minus h times x minus h plus k. I will make a note here that this will be on your formula sheet. So this is just to illustrate where it came from. So it's a good exercise in kind of algebra, but it's just for fun. A times x is a times x squared minus xh minus xh plus h squared plus k. Collect like terms, I get a times x squared minus 2xh plus h squared plus k. This I want it down here. Expand the a inside. I get ax squared minus 2axh. I tend to have variables together and the coefficients out front, but you could have minus a2xh if you want, plus ah squared plus k. Oops. I'm going to copy this to the next page. If you group these, collect like terms of x's, right, then you can rewrite this as ax squared plus negative 2axh plus ah squared plus k. If you want to mimic ax squared plus bx plus c, I would rearrange the second term, right, as negative 2ah times x. And so I would get ax squared plus negative 2ah times x plus ah squared plus k. A is just a in both scenarios. Notice a is a in both. So that's nice. B is equal to negative 2ah. And C is equal to ah squared plus k. This looks somewhat familiar because we had h is equal to what? B divided by negative 2a, or some version of that. Negative b over 2a, just floating that negative up front. So here, how can I? Yep. Solve for h. In b is negative 2ah. We get h is b divided by negative 2a, or h is negative b over 2a, floating that negative out front. Which means what? You can find the or the x coordinate of the vertex, that's your h, by taking negative b over 2a from the standard form. So that's kind of neat. Then, a little bit sneakier now, right? If we think about, let's have some function like this. The vertex is at hk. So h is the x coordinate at the vertex. which means that k is really just the function evaluated at h. Therefore, k is the function evaluated at h. Which we didn't take it any further here. K is the function evaluated at h, which is really the function at negative b over 2a, right? Here, that negative has been floated up top. As long as you only have one negative, it can float from the bottom to the middle to the top, but just one negates it either way. Okay. Let's see. We can do one. What if we have to find the vertex of 2x squared minus 12x plus 1? This is in standard form, which means the first thing I'm going to do is I'm going to figure out what my ax squared plus bx plus c. So I have a is 2, b is negative 12. You don't want to forget that negative. And c is 1. You have on your formula sheet, or you will, but also we just established that h is negative b over 2a. So h is negative b over 2a. So if I have b and a, then I can find h. H is negative 12 divided by 2 times 2. So h must be 3. K, let's do, so from here, K is G at H. The function evaluated at H, which is 2 times 3 squared minus 12 times 3 plus 1. 2 times 9 minus 12 times 3 plus 1, I get negative 17. Therefore, the vertex HK is at 3, negative 17. How can we check that? Can you use Desmos? It's probably the easiest way. I'm going to graph 2x squared minus 12x plus 1. Then I'm going to make sure that it is at 3, negative 17. Snag that. No. Did it. Pretty fun. And there, because I'm over time, I think. You have any questions, let me know. Otherwise, I'll see you here for the test on Thursday.